The idea with sigma notation is that it's a sort of compacted way of writing. I'm adding up this expression multiple times for this range of numbers. So as an example, if we just did a numerical example, like if I had something like this, if I had from like 3 to 1 of, and we can do this expression here, right? So r plus 1. What that's saying is basically, okay, let's sub in r equals to 1 in here. What do I get? So I get 1 times 1 plus 1, or 2, plus, then what's the next thing in the sequence? Yeah, 2, right? So I substitute in r is 2, so I get 2 times
pretty much what the one with n is saying.
2 plus 1, and then I would do 3 times 3 plus 1. So I should write that as 1.
So pretty much just saying do whatever you get n, and n sort of like just a number.
Yeah, right. So some arbitrary kind of value. Here, it's like a defined sequence, defined series, right? Because you're adding them all up, you get from one value to another. This one, it's like a general sense. Hey, I'm saying that I can write it like this. And the same induction process applies, right? Because we want to prove that this is basically a summary of all the sum values. In the sense that, okay, what if we usually test for n equals to 1, and that's what I'm still going to do here, right? So for n equals to 1, for example, if I'm going from like 1 to 1, that's just this first one, right? Yeah.
It's just a fancy way of writing it.
It is a fancy way. It's an easier way of writing it, because I think usually you start, what they would do in an induction question before is they would write out something like this. It's a bit longer, and they have like all these dots and stuff, and then they get the end, or you can just write it in this. It's like a summary, basically. Yeah. But this is, yeah, and they're saying that this expression here represents the sums for this many terms. That's why they have n over here, right? So if I checked for here, what is this? If I add these all up together, let's just check, right? Okay, so that's going to be 20. And so if I put n equals to 3 here, right, that's saying that should be the same. So we get 3 times 3 plus 1 is 4, 5, divided by 3, yeah, and so I do get 20. So you can see the idea with what this expression is really saying, right? How do you prove it through induction? Similar process. So we still have our steps. I know you love steps, don't you? Okay, so how would you prove it true? Well, we know that this guy here, right? If I'm just taking the n value of 1, the left-hand side, that's just going to be equal to 1 times 1 plus 1, which would just be 2, as we've established over there. The right-hand side is going to be equal to 1 times 1 plus 1 times 1 plus 2, all divided by 3. And that's just 6 divided by 3, which is just 2. And it's the same as LHS, right? It works, woohoo! All right, now this is where it starts to get interesting. So we want to assume true.
Step 1's always just like a...
It's a bit of a give me, hey? Like a pat on the back, you did well. So we're going to assume true for n equals k. Now, what's that going to look like? Well, we're working with sigma notation here right now. So we're saying that from the sum of r equals to 1 up to some k value, right? And then these r values still stay here, right? Because this expression is not in terms of n, right? It's saying the current value, I go up to n, or I go up to k in this situation, right? So it's r plus 1 is equal to, now this is where it changes. K outside of k plus 1, k plus 2, all divided by 3. So that's what I'm allowed to assume. What I need to prove is this now. Right, I need to prove that I can write this expression, so I have to be required to prove this, the sigma of r equals to 1 up until k plus 1, and it's going to be equal to this. Right, so I'm replacing all the n's I see with k plus 1. So I'm going to get k plus 1, k plus 1 plus 1, k plus 1 plus 2, all divided by 3. Now at this point here, you may be thinking, hey, I can just write this as k plus 2, and you'd be right, you can do that if you'd like to. So that could just be k plus 2, and that could just be k plus 3. And you could write it in that way, yeah. I guess the tricky thing about this one is thinking about, all right, well, I know that usually I look for what's in step 2 and trying to put it into step 3. I guess it's a bit less clear how you do that in this case, right? And the trick to doing something like this is that we have to break up the sigma notation. In the same way that like with the previous examples, you have to do a bit of manipulation, the same thing applies here, right? So what I want to do is I'm just gonna, let's go. I guess the question is, where can I see this inside of this, right? And if you think about it, go back to this number definition of what's going on here, right? All this is saying is that I'm adding from 1 to whatever this value is, in this case k and k plus 1. I'm adding all the terms after that, and then I can write that as this.
It'll take a while, yes.
Yeah, okay.
Is it the one up there?
This one?
So like the answer to that though?
This one here? Yeah.
Yeah, that.
Yeah.
So the left-hand side for step 3 is that plus
Yeah.
k plus 1 outside of k plus 2. K plus 1, k plus 2.
And how did you get that?
With my brain.
With your big brain.
Yeah.
Right. It's exactly right, actually. And the way you do that and the way you write it out is, I like the thinking, is that basically, if you went from this one here now, if you went from the sigma r equals to 1 to 4, yeah, you're going from all the ones from 1 to 4. But what you could do is you could say that that's the same as, well, all this is adding one extra term, right? What term are you adding? You're adding it when you get r equals to 4, right? So if I was going from that to 4, I would say that that's just equal to, oh, so I have to add in now when r equals to 4, so 4 outside of 4 plus 1. So this is the only extra term that's being added. So in terms of a sigma notation, you could say that that's the same as when I'm going from 1 to 3, and then I just add this extra term, yeah. So that's exactly what you did, and this is exactly what you can do. So I'm going to say step 3, so LHS is equal to this. And then as you said, well, actually, right, I can write this as k outside of sigma r equals to 1, r plus 1. And then I'm going to add, and the way I'm going to write it is I'm going to write it as you said, k plus 1, k plus 2, because that's what you get when you sub k plus 1 into this, right? You get k plus 1, k plus 1 plus 1, which is 2, when you sub in this into this expression, yeah? So that's k plus 1, k plus 2, all right? And then, because this is where the part where we use step 2, because I have this expression here now, I can say that that's just k outside of k plus 1, k plus 2, this is where it gets a bit more algebraically manipulative. What can we do with this?
Oh, wait, so what are we trying to prove?
Exactly, we're trying to get to this.
I'm trying to get to that.
Yeah, so there's something on 3 here, which I like.
I think, yeah, so I think we put under a common
Denominator?
Yeah.
Yeah, you can try that?
Usually it helps.
Yeah, let's try to do it. So what do I get?
So you have the same thing on the left up. And then the next one's going to be 3 over, 3 that stuff.
Yep. Alright.
I mean, I guess you can just go all 3 now. But here's what gets interesting. So we have to have a common factor there. Oh, yeah, easy.
Yeah, what do you do?
You just take out k plus 1,
Yeah.
and then it gets k plus 3.
So these two are in common, and so you get k plus 1, k plus 2, outside of k plus 3, that's what you get left with when you divide these out from each term, all over 3, and that's exactly what we wanted here, right? Awesome. So, which is equal to RHS, right? And then write a nice little conclusion statement, nothing too long, therefore, true by the process of mathematical induction.
This is what I like about math induction. I like doing it because when it works, it's like satisfying.
And you always know when you get it right, yeah?
You do. But then when you don't get it right, remember that one question you got? Everyone was like...
Which question was that one?
It was that one, like it was back in year 11, I think me and Angus would groups would in teams.
Oh, okay. Oh, the one where it's like, it's not, you just go to the next one. Like you have to do a funny one. Yeah, yeah.
Figure it out.
That was a good one, eh?
Yeah.
Yeah, it's very frustrating when it doesn't work, but yeah, great when it does, eh? Cool.
Yeah.
All right, and that's sigma notation. Halfway there.